Good morning, students. Good morning, students. So, now we'll continue again with unit number 3, and this is the last topic for unit number 3, which is important definitions on design capacity of an irrigation canal. So, last class I gave an assignment. So, the question was this, and related to the question I'm giving you the answer for that question. So, gross commanded area for a distributor is 6,000 hectares, 80% of which is cultivable irrigable. The intensity of irrigation for Rabi season is 50% and that for Kharif season is 25%. So if the average duty at the head of the distributor is 2,000 hectares per cubic for Rabi season and 900 hectares per cubic for Kharif season, find out the discharge required at the head of the distributor from average demand considerations. So the solution is GCA is equal to 6,000 hectares, which is already given. So CCA will be 6,000 into 80 by 100, which is equal to 4,800 hectares. So area to be irrigated in Rabi season will be CCA into intensity of irrigation. So CCA we got for 4,800 and intensity of irrigation was given for Rabi season 50%. So 50 by 100, which is equal to 2,400 hectares. Next, area to be irrigated in Kharif season, same formula, CCA into intensity of irrigation. CCA is equal to 4,800 and Kharif season's percentage was 25%, so 25 by 100 and the answer is 1,200 hectares. So water required at the head of the distributary to irrigate Rabi area is 2,400 divided by 2,000 cumecs, which is equal to 1.20 cumecs. So water required at the head of the distributor to irrigate Kharif area is 1,200 by 900 cumecs, which is equal to 1.33 cumecs. So thus the requirement in Kharif season is 1.33 cumecs and that in Rabi season is 1.20 cumecs. The required discharge is maximum of the two, so the answer will be 1.33 cumecs. Hence the distributor should be designed for 1.33 cumecs discharge at its head from average demand considerations. So the head regulator should be sufficient to carry 1.33 cumecs and in Rabi season only 1.20 cumecs will be released. Next, continuation to our previous topic, previous class, important definitions related to canal irrigation design. Next one is net and gross sown areas. So sometimes two crops in two seasons are grown during a particular year on the same area. Hence, such an area will be sown more than once during a given year. If this area is added to the area which is sown only once, which is called the net sown area, then we get what is known as the gross sown area or the gross cropped area. Hence, gross cropped or gross sown area during a year, a particular year, is equal to net cropped area. That is, area sown once in a year plus area sown more than once during the same year. Next definition, net and gross irrigated areas. So based on the above analogy, the area which is irrigated once during a year is called the net irrigated area. And when to this is added the area irrigated more than once, we obtain the gross irrigated area. So therefore, gross irrigated area in a given year is equal to net irrigated area, which is the area irrigated once in a year plus area irrigated more than once during the same year. Next, area to be irrigated. The area proposed to be irrigated in any one crop season or over any given area is called the area to be irrigated in that season or the year respectively. It is obtained by multiplying CCA by the seasonal or annual intensity of irrigation, as the case may be. So the areas to be irrigated are usually worked out separately for each crop season because the water requirement of the crops of those seasons are quite different. Next, time factor. To check the dangers of over-irrigation leading to waterlogging and salinity, no distributor is allowed to operate on all the days during any crop season. So the ratio of the actual operating period of a distributor to the crop period is called the time factor of the distributor. For the Bhakra canal system, for example, the time factors for Kharif and Rabi seasons are fixed at 0.80 and 0.72 respectively, which means that each distributor would receive its full supply for a period of 0.80 into 180, which is equal to 144 days, and 0.72 into 180, which is equal to 129 days, respectively, in each crop season of 180 days. So for computing the design capacity of a distributory, therefore the computed water requirement for the crops proposed to be grown and irrigated by that distributory should be divided by the time factor, since this factor is less than 1. Capacity factor. The capacity factor of a canal is the ratio of the mean supply discharge in a canal during a period to its designed full capacity. Since canals have to run almost to their full design capacities during Kharif season, this value usually varies from 0.9 to 0.95 for Kharif season. However, since water requirement during Rabi, that is winter season, reduces to about 2/3 times, the full supply, the capacity factor usually varies from 0.60 to 0.70 for Rabi season. To improve this factor during Rabi season, the cropped area in Rabi season is hence usually increased. The next term is full supply coefficient. So full supply coefficient is the design duty at the head of the canal. In other words, the number of hectares irrigable per cubic of the canal capacity at its head is known as the full supply coefficient of the canal. It can hence be represented by the equation full supply coefficient, which is equal to area estimated to be irrigated during base period divided by design full supply discharge at the head of the canal. So this factor is also called or also known as the duty on capacity. Next, nominal duty. It is the ratio of the area actually irrigated by the cultivators to the mean supply discharge let out from the outlet of the distributory over the crop period. For example, let small x cubic of water is released daily from the outlet of a distributory for 100 days, say in a total crop period of 125 days. We assume this period. Then the mean supply discharge over the crop period will be x into 100 divided by 125, which is equal to 0.8x cubic. So if the area of crop irrigated by this discharge is A hectares, then the nominal duty will be given by A hectares divided by 0.8 x cubic, which is equal to 1.25 A by x hectare per cubic. So for this lecture number, I won't be giving you assignments, so no assignment for this lecture. So please keep that in mind, no assignment for this lecture. I think this is lecture number 21. So now we'll go through a video which is a bit long, but you have to watch it to understand more about canal irrigation and its design, mainly about its design. And now you can give your attendance in the chat box. So that's all for this lecture. Thank you.
the amount of rainfall is not adequate to meet the water requirements of crops. To supplement this deficiency, irrigation is practiced. India has got 1/5 of the world's irrigated area, which contributes to make it potentially one of the richest agricultural countries in the world. Irrigation has been practiced in India from very early times through wells, tanks, and small channels. But the increased demand for food production has resulted in development of various other irrigation schemes. These irrigation schemes mainly consist of storage or diversion structures and distribution systems. In this program, we will cover the distribution systems comprising of open channels. Natural drains that exist on the earth vary in size from tiny hillside rivulets, streams, small and large rivers, to tidal estuaries. The geometry of the natural channels is in general very irregular. But normally, these channels have plenty of water and have their own course. Hence, they do not provide water at the desired location and in required quantities. This has resulted in human intervention with the natural channels and the development of artificial channel networks. These channels are classified according to their method of construction, cross-sectional area, and alignment. The canal is a long and mild channel which may be lined or unlined. The flume is a channel usually supported on or above the surface of the ground to carry water across a different. A channel having a steep slope is called a chute. If the drop in elevation occurs in a short distance, the chute is then called a drop. A covered channel flowing partly full to drain water across the highway and railroad embankments is called a culvert. It could be rectangular or circular. You might have noticed by now that these artificial channels are designed with regular geometric shapes. The trapezoid is the most common shape for channels with unlined earthen banks. Generally, it has stable side slopes. The rectangle. Channels having rectangular cross sections are built of stable materials such as lined masonry, rocks, or timber. Triangular sections are used only for small ditches, roadside gutters, and laboratory works. The circle is a popular cross section for sewers and culverts. In practice, other shapes are also used, where the sharp corners are rounded off. These are parabolas, round cornered rectangles, and round bottomed triangles. Now the question is, which is the most efficient cross section? The efficient cross section is the one which, for a given slope and area, has the maximum carrying capacity. For such a section, the wetted perimeter will be minimum and hydraulic radius will be maximum. For an open channel, the semicircle is the most efficient cross section. However, if the rectangular cross section is chosen, it will be half of a square that is, the depth equal to half of the width to make it the most efficient cross section. If the cross section chosen is triangular, the angle between the side slopes should be 90 degrees. But in practice, trapezoidal sections are mostly used to carry large discharges. Half of the hexagon is the efficient cross section in this category. Channels are aligned so as to permit gravity irrigation in maximum possible areas. The alignment should be such that it reduces the capital investments and maintenance costs and saves the transmission losses. Let us understand the alignment of canals with the help of a model. Irrigation channels are generally aligned with reference to contours. A channel aligned nearly parallel to the contours of the country is called a contour channel. As some contours are higher on one side of the channel, a contour channel irrigates only the other side of the country. While laying a canal system, we may encounter natural drainage such as a river which crosses the canal at right angles. When the drainage bed level is lower than the canal bed level, we construct an aqueduct to carry canal water. An aqueduct is preferred when the drainage is wide and of higher discharge capacity, and the water flows for longer durations. But the situation may be reversed as well. When the bed level of the river is higher than the canal bed level, a super passage is constructed. It is a case when the canal is in deep cutting. However, when the headway clearance between the riverbed and canal supply level is small, a canal siphon is built. The canal water is passed through an inverted siphon under the drainage, and the bed level of the canal is raised again on the other side. If the river and canal are almost at the same bed level and the flood discharge is intermittent and large, it would be economical to build a level crossing with regulating structures. In this system, sometimes the canal supply can be augmented with river discharge. After the head reach, a channel aligned along the ridge of a watershed is called a watershed channel. It can irrigate on both sides. Here, cross drainage works are obviated. A channel aligned roughly at right angles to the contours is called a side slope channel. The cross drainage works do not intercept this channel. However, in the alignment of the canal, there may be a situation that we may have to avoid religious places, other monuments, and villages. In order to avoid these obstructions, to fulfill topographical conditions, and for diversion works, curves in the channels are introduced. Curves in unlined canals are made as gentle as possible, since they lead to disturbance of the flow, and they also have a tendency to silt on the inside and to square on the outside of the curve. For the same discharge, the radius of curvature for lined canals is less than for the unlined canals. Effectiveness of an irrigation channel network depends primarily on the command area it serves. Therefore, channels used for water distribution purposes require a high level at the point of delivery to serve the area under command without any difficulty. Normally, the channels with high discharge require less slopes than smaller ones. When the fields are high, adjacent to channels, water may have to be lifted from the channel. The side slopes of the canal depend upon the nature of the soil in which the channel is to be excavated, depth of cutting, and the height of the embankment. Generally speaking, Side slopes should be made as steep as possible and should be designed for high hydraulic efficiency and stability. The minimum slopes usually allowed vary from 1.5:1 to 2:1 for cutting. For loose sand embankments, the side slope ratio varies from 2:1 to 3:1. When canals are dug through rocks, the slopes are kept maximum, varying from 0.25:1 to 0.5:1. In order to allow for fluctuations in water level, a freeboard is provided. The freeboard is measured from full supply level to the top of the bank. The amount of water that we feed in a channel does not reach the fields. A major portion of the water is lost through seepage. The seepage losses constitute 35 to 50% of available water at the canal head. Seepage losses are considerably reduced by lining the canal. Lining also prevents waterlogging, weed growth, and reduces silting and erosion in the canal. Various types of lining can be mainly grouped into two categories: exposed and hard surface linings, buried membrane linings. The initial cost of exposed linings is generally high. They are recommended for use where structural safety is the primary consideration. There are several types of linings. Thick compacted earth lining may prove to be economical where suitable material for construction is available at site. Boulder lining is another economical lining where boulders obtained during excavation are readily available. It has very little flexural resistance or flexibility. Such lining is not satisfactory for canal infilling. Brick lining has been extensively used. It has the advantage of low initial and maintenance costs and quicker construction. Cement concrete lining is preferable because of its greater resistance to erosion and where the channel is to carry high velocity water. Precast concrete tiles are more compact and impervious. These tiles are laid in 1:3 cement mortar in single or double layers directly on the compact subgrade. In shotcrete lining, cement mortar is applied by pneumatic pressure. It can be placed over rough subgrade. Sandstone lining is used in field channels depending upon its availability and cost effectiveness. Plastic film and a layer of bentonite protected by earth or gravel cover are cheap linings. These are commonly recommended linings. But the drawback in membrane linings is that it is susceptible to damage by weed roots. In this case, permissible water velocity is also limited in order to avoid erosion. Out of so many types of linings, what are the criterion used in the selection of a lining? We put this question with reference to the modernization of the Upper Ganga Canal to Shri R.C. Goel, Chief Engineer, Irrigation Department.
The basic criteria are two: cost and the time that we use in their construction. As I said, concrete lining is definitely faster to do when using bed. And cost-wise, concrete lining in the bed is a little cheaper also. But if we were to do concrete lining on the slopes, though the materials cost would be comparable, but the labor cost would increase. Also, it needs shuttering and all that. Initially, we started with concrete lining because we had the experience of it and it could be readily started. Then later on, we established a factory for concrete tiles. Side by side, we started a new kiln factory to build up clay tiles. In fact, in this area, ample aggregates sand is available, River Ganga, but concrete tiles are not that impervious as the clay tiles. Clay tiles are definitely far, far better in respect of abrasion and imperviousness. So now we are doing concrete lining in the bed, and most of the slopes we are having double tile, clay tile line. By making a new lined canal, we are saving very substantial quantities of water to the tune of 240 million cubic meters, which will result in very substantial increases in agriculture production.
Now, the water is to reach the fields. For this purpose, we have a canal irrigation network. A canal which takes off directly from the headworks is called the main canal. Normally, no irrigation is carried out from a main canal. A canal taking off from the main canal is called a branch canal. Distributary channels are taken off from the branch canal and sometimes from the main canal. A distributary can be a major or a minor, depending on the discharge. Water courses are small channels, generally constructed by cultivators themselves. They run from outlets provided in the distributary channel and convey water to field channels. For water distribution, it is necessary to adjust the discharge in a channel to any known value. This adjustment is carried out by the regulator at the headworks. In this process, sometimes it becomes necessary